Okay, so now we're going to look at all the theorems that are on the Junior Cert course. Okay, you're going to look at how you prove them. Okay, there are specific layouts for the ones that you have to prove formally. And we're going to look at the axioms and the corollaries that are on your course as well. So firstly, we're just going to look at some terminology. Okay, so you could be asked what any of these are in an exam situation. Okay, so you do need to understand what they're looking for. So a theorem, it's a statement which has been proven to be true by following a number of logical steps or by using other theorems or axioms. Okay, the converse, so the converse of a theorem then, that's just the reverse of a theorem. So by taking the conclusion as the starting point and having the starting point as the conclusion, you're just reversing around whatever the theorem states. Okay, like for example, there's a theorem that states if two sides of a triangle are the same, then the triangle must be isosceles. Alright, the converse of that would be in an isosceles triangle, the two sides are the same. You know, it's just the reverse of each other. An axiom then is a statement which you accept to be true without any proof. Okay, so there is one particular line through which 2 points would lie. You just take that to be true. It's a statement which is taken to be true. A corollary then, a corollary is something that will follow on after a theorem. Okay, so it has to be true because if it's already been proven in that theorem, it's a given result. Okay, like you might go off and prove that the three angles of a triangle add up to 180 degrees. So the axiom would be that three angles in a triangle add up to 180 degrees. Okay, it's a statement then that you accept to be true, and you don't need to go off and, it's a statement that you accept to be true because it follows on from the theorem. So you don't need to go off and reprove the theorem or anything like that. The word implies, so that just indicates that a logical relationship exists between two particular statements, such that if the first is true, well then the second must also be true. That's what the word implies means. There's the symbol, okay, so that little symbol there is for implies. A proof then, it's a sequence of statements consisting of axioms and assumptions and any arguments that will lead to the establishment of the truth of one final statement. Okay, so if you're asked to prove something, you would have to have at least 3 lines within that proof to prove that it's true. And usually the proofs come up when we're trying to do congruency, okay, proving that triangles are congruent or something to that effect. Okay, so on your course there are 5 axioms that you just need to know. Okay, you don't need to learn them off by heart or anything, you just need to know them and understand them. Okay, so the first one there, axiom 1, 2 points, so there is exactly one line through which any 2 points would lie upon. That's just a given statement that you know to be true. Alright, so the points A and B lie on that line, and there's only one line that will go through those 2 particular points. There isn't another line that could go through the 2 points coming from a different angle or something. Okay. Axiom 2, this is the ruler axiom. So the distance between 2 particular points is never negative. Distance cannot be negative. Okay, so that just means the length of AB is equal to the length of BA. So going forwards is the same as going backwards. And if the point C lies on AB, okay, so like let's say this is your line segment A to B. If C happened to be right there, then the distance from A to B, okay, so from A over to B should equal the distance from A to C and plus the distance from C to B. That's all that's stating. Again, that's not something you need to learn off by heart or anything, it's just something that we need to know, okay? Distance can never be negative. Okay, axiom 3 is the protractor axiom. So the number of degrees in an angle is always going to lie in between 0 and 360. A full rotation is 360 degrees. So all angles at a particular point would add up to 360. So if we look at that little diagram there. Okay, so 30, 150, 30, 75 and 75, they will all add up to be 360. So all angles at a point will always add up to 360. If an angle is divided into 2 smaller angles, then these 2 angles would add up to be the original angle. So again, down here, if you add angle 1 and angle 2, you would get angle 3. Again, we know these things, they're pretty obvious. Axiom 4, that's just congruency. Okay, we've got 4 axioms of congruency: side, angle, side, angle, side, and right angle, hypotenuse, and one other side. Okay, so congruent triangles are identical triangles. That's axiom 4. And the 5th axiom then is for parallel lines. So given any line L and a point P, there is exactly one line through P that would also be parallel to L. Okay? There's no other line that I could draw going through P that would make it parallel to L. It's only this one. Right? There'd be no point in drawing a line going through P like this, because that line would not be parallel to L. Alright, so there are your 5 axioms. Again, it's not that they need to be learnt off by heart, you just need to understand them, and we know most of them anyway. We've come across them. Okay, there are 19 theorems on your course. Now, of the 19, only the following ones have to be formally proven. Okay, these are the ones that could come up in the exam papers as a full question. And they are theorems 4, 6, 9, 14 and 19. Okay, you obviously need to know all the theorems, as in you need to know how to use them and how to apply them in questions. But the ones that you formally have to prove are these 5 theorems. Okay, so theorem 4, 6, 9, 14 and 19. Now I'm going to flag them as I go through them. I'm going to flag the theorems and I'm going to star the ones that are the formal proofs. Okay, so you have to be able to go through all of those line by line. Okay, so this is the layout for a formal proof. So up at the very beginning, you give your title of the theorem, whatever the theorem is, okay? It could be that the exterior angle of a triangle is equal to the sum of the 2 interior opposite angles, right? That would be your theorem. Then what are you given? So what was given in the question plus any diagrams that you might have to draw. Then the next stage would be to prove. So what is it that you're actually trying to prove? And plus any properties of what you are trying to prove. Property might be, you know, if you have to prove that this side is equal to this side, or this angle is equal to this angle, or whatever it is that you have to prove. Then there's a construction. So based on whatever diagram that up here that you have given, okay, now this is a diagram that you'll be giving yourself. It's not that it's given in the question, you'll have to give it usually. In the construction part is, if you need to add on any lines or angles or whatever to the diagram that was up here, this is where you do it, okay, at the construction stage. So you construct any additional lines or angles and you label them clearly and you state what it is you're constructing. You know, if you were constructing, dropping a line from this point to this point or whatever you're doing. And then the last part is the actual proof. So within your proof, one reason or statement per line in order to prove what you've been asked. Okay, so you can't make a statement without a reason to go with it. Like you have to back up your statement. Like, how do you know this is true? What's the reason for it? Like if you're saying this angle is equal to this angle, well, why? Are they vertically opposite? Are they alternate? Are they corresponding? Or, you know, what's the reason that they're equal? So that's the layout of a formal proof of a theorem. Okay, so you need to know that layout off by heart. Okay, so let's start then. Okay, right, so theorem 1, vertically opposite angles are equal in measure. We know that anyway, okay? That's not a formal proof. We know that vertically opposite angles are equal. Theorem 2, in an isosceles triangle, the angles opposite the equal sides are equal. Again, we know that to be true for isosceles triangles. So the opposite sides are equal and opposite angles are equal in an isosceles. That's theorem 2. And just as well, quick note, you don't need to know the numbers of the theorems off by heart or anything like that. Like you're not going to be asked, state theorem 14. They'll give you the actual name of the theorem so you know what one you're working with. Okay, so you don't need to learn off the numbers of these theorems. Okay, so theorem 3, if a transversal line makes equal alternate angles on 2 lines, then the lines must have been parallel. And the converse of that is also true. So basically that if 2 lines are parallel, well then the angles on opposite sides of the transversal would be equal. That would be the converse. So here's my 2 parallel lines. Angle A is alternate to angle B. You can see form the Z shape. And this dot here, this angle, is alternate to this angle. Look at the Z shape. Okay, that would tell us then, if I'm told that A is equal to B and that this is equal to this, that's telling me so that line L must have been parallel to line M. Okay, so that's theorem 3. And the converse, if you're told that line L and M are parallel, well then you can automatically assume that angle A and B are equal and these 2 angles are also equal. Now, theorem 4 I have started because this is a formal proof. Okay, and it's one of the shorter ones. Okay, the angles in any triangle add up to 180 degrees. Right, so you would start off with what you have been given. So that's the title of your theorem, okay? The angles in a triangle add to 180. Next then, what is it that you have been given? So you won't be given anything, you'll have to give it to yourself, right? So draw this diagram, okay? What I have drawn in black, so the D and the E will not be visible yet. So you draw a line L and M that are parallel to each other, and you draw in a triangle and you label the angles A, B and C. right? That's what you would have been given. Now, what are we trying to prove? We're trying to prove that angle A plus angle B plus angle C is equal to 180 degrees. That's what we're trying to prove. Construction. So the construction then would be label angle D and E. That would be your construction part. So I've done that in a different colour pen. So that's in green. Label angle D and E. And then to prove. So this is where you start proving it out. So this is this part here. Right, okay, so L was parallel to M. That was what we were given up the top, right? So we've been given two lines that are parallel, L and M. Now, angle D is equal to angle A. The reason, because they are alternate, because of the parallel lines. Angle E and angle B are also alternate to each other, so they're the same as each other. So you could basically call D A and you could call E B if you wanted, because they are the same thing. I also know that angle D, C and E would add together to give you 180 degrees because it's on a straight line. That's your reasoning. And if I know that A is the same as D and E is the same as B, I could technically say angle A, B, C is therefore equal to 180 degrees. And that's what I was trying to prove in the first place, that those three angles add up to 180 degrees. Okay, so that's theorem 4. That's the first formal proof. Theorem 5. Two lines are parallel if and only if, for any transversal, the corresponding angles are equal. So remember what corresponding looks like. Corresponding is if you were to cut out the angle and without rotating it or flipping it or doing anything with it, you could place it directly down on top of another angle. So if you look at this diagram, angle 1 corresponds with angle 5. Angle 2 corresponds with angle 6. 3 corresponds with 7. And 4 corresponds with 8. Okay? Again, this is not a formal proof. Theorem 6. This is a formal proof. Okay, so there's a star on it. Each exterior angle of a triangle is equal to the sum of the two interior opposite angles. Okay, so basically up at the top, that's your title. Okay, then what is it that we're trying to prove? We're trying to prove that angle D is equal to angle A plus angle B. That's what I'm trying to prove. Okay, then what have you been given? So we have been given a triangle ABC and an extended angle D. That's what you've been given. Okay, so given a triangle ABC and an extended angle D. Construction. Label the angles A, B, C and D. That's your construction. Alright, label the angles A, B, C and D. To prove. So this is my proof part. Okay, so we already know that the three angles in a triangle should add up to be 180 degrees. So angle A plus angle B plus angle C is equal to 180 degrees. Angles in a triangle. That's your reasoning. I also know that angle C and angle D are on a straight line. So they should equal 180 degrees if I add them together. Okay, and remember you always have to give your reasonings. So straight angle, that's your reason. Now, the fact that this line equals 180 degrees and this line is equal to 180 degrees, well, if they both equal 180 degrees, well, then that must mean that they are both equal to each other. So that's what I'm doing next. I'm now saying angle A, B and C must equal angle C plus angle D. That's what I've done here. Now, you've got an angle C on both sides of the equation. So they must cancel each other out. If they're on both sides, they'd cancel each other out. And you are then left with angle A plus angle B is now equal to angle D. And that's what I was trying to prove. Okay, so the exterior angle of the triangle is equal to the sum of the two interior opposite angles. So that's theorem 6. Theorem 7, again, it's not a formal proof. The angle opposite the greater of the two sides is greater than the angle opposite the lesser side. Okay, all this basically means in plain simple English is the largest angle will be opposite the largest side. The smallest angle will be opposite the smallest side. Theorem 8. Two sides of a triangle are together greater than the sum of, or than the third side. So if we look at that quick example there, 8 and 7 is definitely greater than 5, that's true. 7 and 5 is definitely greater than 8, that's true. And 8 and 5 is definitely greater than 7, so that's true. Therefore, that triangle can be constructed. Okay, if any of them were false, well, that would mean that the triangle couldn't be constructed. Theorem 9 is another formal proof. Okay, so I've started. Okay, so in a parallelogram, opposite sides are equal and opposite angles are equal. So that's what I'm trying to prove. Okay, that opposite sides are equal and that opposite angles are equal. So again, that's your title. What have we been given? So we have been given a parallelogram ABCD. Okay, so that's what I've drawn in black. So what I've drawn in black is your diagram for the given part. So I've given a parallelogram and labelled it ABCD. Right? I've also shown the parallel symbols, like so that side is parallel to that and that side is parallel to that. To prove, so I want to prove that opposite sides are equal and opposite angles are equal. So, what's your labelling? I want to prove that BC, the length of BC is equal to the length of AD, and that the length of AB is equal in length to CD. And then look at your angles. I want to prove that opposite angles are equal. So I want to prove that angle BAD, right, so this angle here, is equal to angle BCD, this angle up here, and also that angle CBA, so this one here, is equal to angle CDA. So just make sure your labelling is accurate. So that's what I'm trying to prove. So there's a lot of things there that I'm trying to prove. Construction. Draw the diagonal A to C. So that's what I've done in red pen in my diagram. That's the construction part. I drew in the diagonal from A over to C. Proof. Okay, so the fact that I've been given a parallelogram, that means I can look for alternate angles, right? So angle BCA, so BCA is this angle up here with the dot. That is equal to angle CAD. Why? Because they are alternate. I also know that the diagonal, if you split up the diagram, it's two triangles you've split into. Therefore, the side AC is common to both of those triangles. So AC is equal to AC because it's a common side. And then this angle here, so angle BAC, so this one, is obviously equal to angle ACD because they're also alternate. Look at the Z. So the fact that I have now proven that that angle, that side and that angle is the same as that angle, that side and that angle, I've now proven that those two triangles are congruent by angle side angle. Okay, so therefore triangle ABC is congruent to triangle ACD by angle side angle. If they're congruent triangles, that means they are identical. All right? So that means the length of AB is equal to the length of CD, and the length of BC is equal to the length of AD, because they are corresponding sides in the identical triangles. And also angle ABC is equal to angle CDA because they would be corresponding angles in the parallelogram. Okay, so that means this angle up here is equal to this angle here because they correspond. They would have to be the same because they are the third remaining angle in the triangle. Okay, because those two angles already equal to those two angles, so therefore the third angles must be equal as well. Okay, similarly, angle BAD is equal to angle BCD, so that's just the larger one. So this full angle here is equal to this full angle over here, because they obviously correspond as well. So you have now proven what they asked you to prove, QED. Okay, QED just stands for Quod Erat Demonstrandium. That just means what was to be proved is proved. Okay, so that's Theorem 9. Okay, the converse of Theorem 9, remember the converse just means rearrange it, so let's just look again what Theorem 9 stated. In a parallelogram, opposite sides are equal and opposite angles are equal. So if we reverse that, if the opposite angles and opposite sides of a quadrilateral are equal, well then it must have been a parallelogram. Okay, remember not all quadrilaterals are parallelograms. So just for examples, okay, that's quadrilateral. It has four sides. It's not a parallelogram though. Like that side is not parallel to that, and that side is not parallel to that. But it's still a quadrilateral. Okay, so just make note, not all quadrilaterals are parallelograms, but all parallelograms are quadrilaterals. So that's your converse of Theorem 9. Theorem 10. The diagonals of a parallelogram bisect each other. To bisect means to cut in two. Okay, so like this diagonal here intersects this diagonal here at this particular point. That means the length of this is the same as the length of this, and the length of this is the same as the length of this. But take this note, do not assume that the diagonals are equal in length to each other. So what that means is, right, this could be from here to here could be a length of 5, which means that's also a length of 5. That does not mean that from here to here is a length of 5, because that diagonal might have been shorter than this diagonal. Okay, so while diagonals in a parallelogram, they bisect each other, it just means that that is the same as that, and that is the same as that, but it doesn't mean that they're all the same as each other. Okay, so maybe if you put numbers on that, it might make you not make the mistake of thinking that they're all equal to each other. They're not all equal to each other. Theorem 11, if three parallel lines cut off equal segments on some transversal line, then they will cut off equal segments on any transversal line. So all that means is, if I know that A to B is the same length as B to C, well then that's telling me that D to E is obviously the same length as E to F, and over here A dash to B dash is the same as B dash to F dash. That's all it's stating. Okay, so if this transversal cuts equal segments on those three parallel lines, okay, so they're equal segments because they're showing me in the diagram that they are, that's just saying it's cutting equal segments on all transversals. So like this could be a length of 5, then that's obviously a length of 5. That does not mean that this is 5 and that's 5. It just means that whatever this is, that is the same length as it. So if this is 3, that's 3. If this is 10, that's 10. Okay, it doesn't mean that all the transversals are split by the same figure. It doesn't mean that. It just means they're split in the same ratio. Theorem 12. Let ABC be a triangle. If a line L is parallel to BC and it cuts AB in the ratio of m is to n, then it also cuts AC in the same ratio. This is just when we did similar triangles. Okay, the ratio of their sides are in proportion. So you can see this line is parallel to this line. So like that's a little triangle in itself, and that's the larger overall triangle. That just means that AX all over XB would be in the same ratio as AY all over YC. Okay, normally how we do similar triangles is we split up the triangles into two and we draw them separately, which is Theorem 13. So if two triangles ABC and DEF are similar, well then their sides are in proportion to each other. So let's just look at those two diagrams there. They're similar because they're equiangular. Okay, similar triangles, they're similar, they're not identical. Okay, they're similar because their angles are all the same. So like angle A is the same as angle D, angle B is the same as angle E, and angle C is the same as angle F. Therefore, I can say the corresponding sides, if you want to use a highlighter, AB should correspond with DE, AC should correspond with DF, and BC would correspond with EF. Therefore, I can use this ratio. Big over small equals big over small, just be consistent. So AB all over DE should equal BC all over EF, which should equal AC all over DF. Okay, or you could do it the other way around if you wanted. Okay, you could do small over big, in which case this would end up being DE over AB, this would be EF over BC, and this would be DF over AC. Just as long as you're consistent. If you're going big triangle over small triangle, you remain consistent the whole way through. Okay, so that's all that's stating. Theorem 14 is a formal proof, so I've put a star on it. Okay, so the theorem states, it's the theorem of Pythagoras. So in a right-angled triangle, the square of the hypotenuse is equal to the sum of the squares on the other two sides. Okay, so that is your theorem of Pythagoras. Right, so what have we been given? We have been given a right-angled triangle, and I've labelled it as ABC. Okay, so I might just come down here and do it off the sheet instead. It's clearer. Okay, so I've been given a right-angled triangle, ABC, with the angle ABC 90 degrees. Right, so there's my diagram. That's what I've been given. Construction, or sorry, what am I trying to prove first of all? Well, I'm trying to prove Pythagoras' theorem. So basically that, the hypotenuse, which is AC, square that, and that should equal BC to be squared plus AB to be squared. So that's what I'm trying to prove. Now, construction. Draw BD perpendicular to AC. So I'm dropping a perpendicular from this vertex B down to the side AC. Okay, it's completely vertical, which means it's creating a 90-degree angle here and here. Okay, so that's your construction. You can do it in red pen if you want to show that it's the construction part. Okay, then the proof. Okay, so what do we know so far? We know that angle, and your labelling is really important, girls. Angle ABC equals angle BDC because they're both 90 degrees. Okay, so angle ABC, so this big angle up here, this was 90 degrees, And I also know that angle BDC is 90 degrees, okay? So that little one there. Angle BCA is equal to angle BCD. So BCA, so this angle here, is equal to angle DBC, so DBC, because they are a common angle. All right. Now, what I mean by that, like I suppose if I drew out the two triangles, I suppose it's harder seeing it from that construction. If I draw them out separately here, it's easier to see it. So I've drawn out the big overall triangle, which is ABC, and then the smaller triangle on the right, okay, DBC. So that's what I've drawn them out. And I've just labelled what's what in each of them. So there was the right angle in the bigger triangle, and there's the right angle in the smaller triangle. There's angle C here is a common angle to this angle here. Okay, so angle BCA is a common angle with angle BCD. Okay, and then what else do I know about this? So angle BAC is equal to angle DBC because they would both have to sum to be 180 degrees. Okay, so if I know that this is 90 degrees and this is whatever it is, the two of those are the same as that 90 degree angle and that 90 degree angle. So that's just telling me that the third angle where I've placed a dot, that third angle must be equal to that third angle. So that's telling me that the two triangles are equiangular. They share all the same angles. Okay, so that remaining angle is equal because the the two triangles end up summing to 180 degrees each. Okay, so therefore triangle ABC is similar to triangle BCD because they're equiangular. That's why they're similar. They're not identical, they're just similar. Okay, so now once I've done that, you can match up corresponding sides. So AB, look for the angles. I'm looking for the dot and the right angle. So this side here, which I put 3 little strikes on, that corresponds to, there's the dot and the right angle in the other triangle. So that corresponds with that side. So put the same symbol on them. Then look for the right angle and this angle, and I've put 2 strikes on that. So there is the right angle and this angle. So there's 2 strikes. And then the third side, the dot and this angle, there's the dot and there's this angle. So those 2 sides are corresponding. Okay, so you can use a highlighter to do it if you want. I've just used little strikes. So now I'm matching up the corresponding sides and I'm writing them as a ratio to each other. And that's coming from knowledge from Theorem 13, that the ratio of sides should be in proportion in similar triangles. So I'm going with big over small, okay? This is the big triangle, that's the smaller one. So this side over this side, so that's AC over BC, should equal this side over that side, so AB all over BD, which should also equal the third side, okay, BC all over DC. Okay, so that's my ratios. Now, looking at this, I am going to use this ratio and this ratio. The reason I'm using the two of those and the reason I have those underlined is because both of those contained a BC. Okay, so I'm going to use those. You can circle them, okay, or you can underline them. I'm going to use 2 of those because they both contain a BC. The reason I want those is because back up in what I was trying to prove, I have a BC to be squared. So I know that's why I'm going to be using those 2, right? So if they're all equal to each other, that means AC over BC is obviously equal to BC over DC as well. Okay, the order doesn't matter. So I'm now writing down the 2 of those are equal to each other. Next, I'm going to cross multiply. So I'm bringing up the DC and I'm multiplying it by AC, and I'm bringing up the BC and I'm multiplying it by BC. Okay, so I've got BC by BC is equal to AC by DC. BC multiplied by BC is BC all to be squared. And that now equals AC multiplied by DC. And I've put that in a box because I'll use it later on. Okay, so I now know that BC to be squared, I can use that up here. Okay, because that's what I'm trying to prove. Now, we're back to the diagram that I did my construction on. Okay, so we're back up to this. Now, what I have just proven as part of my proof is I've proven that the overall big triangle is similar to this little one here. What I am now going to do is I'm going to prove that the overall big triangle is also similar to this one here. Okay, so this triangle. And it's going to be the same type of proof again. Okay, so draw the 2 of them out separately. This is ABC, the overall big triangle. And this is the smaller triangle to the left, ABD. So I've drawn them out separately. Again, I'm marking in what is what in both triangles. They both share that common angle A, so I've put a dot in it. They both had a right angle, Okay, label that, which means their third remaining angles must be equal as well. Now that I know all the angles in both triangles, I'm going to match up their corresponding sides. So you can use your highlighters if you want. The right angle and the dot is that side. There's the right angle and the dots, that's that side. So they correspond. So AB corresponds with AD. Then BC, so the right angle and this angle, that's BC. That should correspond with the right angle and this angle, so there's BD. They correspond. The third remaining sides obviously correspond then as well. AC, which is the dot and this angle. AB, the dot and this angle, so they correspond. Okay, so now that I know that they all correspond, I'm writing them, or I'm writing out the information. So I'm now considering those two triangles. Okay, ABC and ABD. Angle ABC equals angle ADB because they're both 90 degrees. Angle BAC is equal to angle BAD because they have a common angle, right? So those two angles were shared, they're a common angle. Angle BCA is equal to angle ABD because the third remaining angle in the triangle should be equal. Okay, because all the angles have to add up to 180 degrees. So that's just stating that that angle there is obviously the same as that angle there. Therefore, triangle ABC and triangle ABD are similar because they are equiangular. Okay, they are not congruent, they are similar. So the fact that I now know they're similar, I can write the ratio of their sides in proportion to one another. So AB, big over small again. AB over AD is equal to AC over AB, which equals BC over BD. And again, that's just coming from my knowledge of the ratio of sides being in proportion from Theorem 13. Again, I'm underlying what I see common in that whole equation. So look, there's an AB there and there's an AB there. So I'm going to use the two of those. All right. So in using the two of those, I'm ignoring that third one. I don't need it. I'm going to use those two, okay, and I'm going to cross multiply. So it's going to be AB multiplied by AB is equal to AD multiplied by AC. AB by AB is AB to be squared. So AB squared is equal to AC multiplied by AD, and I've put that in a box. Okay? Now, remember what it is I am trying to prove. So back at the beginning of my proof, I was trying to prove that AC squared is equal to AB squared plus BC squared. Well, I know what BC squared is because I did it down here, and I put it in a box. There's BC squared. I also now know what AB squared is because I have done it over here. There's AB squared, so I'm going to use the two of those now and I'm going to add them. Okay, so AB squared plus BC squared. This was AB squared, AC multiplied by AD, plus this is BC squared, AC multiplied by DC. Now, there's an AC common to both of these terms, so factor out an AC and open a bracket. AC goes into AC by AD, AD times. AC goes into AC by DC, DC times. Okay, now look at your diagram. The length of A to D plus the length of D to C. So look back at your diagram. A to D is here and D to C is there. So if you add the length of A to D and the length of D to C, aren't you technically getting the length of AC in total? So I'm just going to substitute that in instead. So AD plus DC is technically the length of AC altogether. Okay, since AD plus DC is AC. So now I have AC multiplied by that, which is actually AC multiplied by AC. And AC by AC is AC to be squared. I have now proven what I was trying to prove at the very beginning of my theorem. That AC squared is equal to BC squared plus AB to be squared. Okay, so that's now proven. Okay, so Theorem 14, it is quite a long proof. Alright, so do practice it quite a few times to get your head around it. Okay. Right, next I'm going to look at the converse then of Theorem 14. So if the theorem itself stated, just go back. The theorem itself stated that in a right angled triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. Well, then the reverse of that would be the converse. If the square on the longest side of the triangle is equal to the sum of the squares on the other two sides, then the triangle is a right angled triangle. Okay, Theorem 15. If the square of one side of a triangle is the sum of the squares of the other two sides, then the angle opposite the first side is always a right angle. Okay, so basically, longest side opposite the right angle. That's all it's telling us. Theorem 16. For a triangle, the base times the height does not depend on the choice of base. So let's look at the first triangle here. If that's your base, that's your perpendicular height. Okay, and you could go off and get the area of it, half the base by the perpendicular height. If this is the triangle and you're using AB to be the base, well then this is your perpendicular height. And the third one, if you were using this as, if you're using this as the base, well then this is obviously the perpendicular height because it is at a perpendicular angle. Okay, they are all the same triangles, which means they all have the exact same area. So whatever base you choose, your height will depend on the base. Okay? Theorem 17. A diagonal of a parallelogram bisects the area. So whatever the area of that parallelogram is, where you put in a diagonal, that means it has bisected the area. It's cut it in two. So the area of this triangle should be the exact same as the area of that triangle. That's all that's stating. Theorem 18. The area of a parallelogram is the base times the height. Okay, so there's your parallelogram. Whatever the base is, there's your perpendicular height. If that's your base, that is still your perpendicular height. Whereas this is a slant height, right? So you wouldn't be using that. Now, Theorem 19 is a formal proof, and it's the last theorem on your course. The angle at the centre of a circle, standing on a given arc, is twice the angle at any point on the circle, standing on the same arc. So it's quite wordy. Okay, so just make sure you read it again to yourselves. Okay, so what I'm trying to prove here is this angle here is going to be twice that angle up there. That's what I'm trying to prove, basically. Okay, so what have I been given? A circle with a centre O and an arc A to C. So there's the circle. It has a centre O, and this is the arc AC. So I've labelled A and I've labelled C. A point B is on the circle. There's the point B. Okay, and I've just joined them all up. What am I trying to prove? That angle AOC equals twice angle ABC. Angle AOC is equal to twice angle ABC. Construction. Join B to O and extend it to a point D, and then label the angles 1 to 6. So there's your construction. You can do any construction lines in a different colour pen just to make it look like it's not part of the original diagram. So I've extended a line from B going through O and extended it out as far as the point D. And then I've labelled all my angles. So 1, 2, 3, 4, 5 and 6. Okay. Now, it doesn't matter what order you label them in. Like, you might have called that one 1, 2, 3, 4, 5 and 6 or whatever. Just as long as in your proof it's consistent with your diagram. Okay. So this angle AOC, I have now broken it up into angle 5 and angle 6 together. So that's all that's stating there. Okay, so the proof. OA is equal to the length of OB because they're both radii. OA and OB, they're equal in length. They're both radii. So that is the same as that. Therefore, it's an isosceles triangle. So angle 1 is equal to angle 2. That angle there is equal to that angle there. Right, angle 5 is equal to angle 1 and angle 2. Why? Because the exterior angle of a triangle is equal to the sum of the two interior opposites. You don't have to write the full thing out. Exterior angle will suffice because I know what you're trying to say. So angle 5 equals angle 1 and 2 added together. So angle 5 is the exterior angle, and that equals angle 1 and angle 2 added together. So the exterior angle of a triangle equals the sum of the two interior opposites. Okay, so now that I know from the second line that angle 1 is the same as angle 2, in the third line, where I'm saying angle 5 equals angle 1 plus angle 2, well, if 1 and 2 are the same angle, I could technically call this angle 2 as well. So that's like saying angle 5 is equal to angle 2 plus angle 2, which is twice angle 2. Okay, so there's your reasoning, because angle 1 and 2 are equal to each other. Similarly, I could also state that angle 6 is equal to twice angle 3. So angle 6, there's the exterior angle, that is equal to angle 3 and angle 4, because they are two interior opposite angles. And isn't this triangle an isosceles as well? Because that's a radius, and that's a radius. So therefore angle 3 and 4 are equal. So if angle 6 is the same as angle 3 and angle 4, and angle 3 and 4 are the same angle, well, I can technically say angle 6 is the same as twice angle 3. Okay, so that's where this line is coming from. Similarly, angle 6 is equal to twice angle 3. And all your symbols are really, really important, angles, okay? Now, angle 5 and angle 6. So look at angle 5 and 6. This is angle 5 and this is angle 6, which is technically angle AOC altogether. So the two of those angles added together is that full angle. But I already know that angle 5 is equivalent to twice angle 2. And I know that angle 6 is equivalent to twice angle 3. So if I add the two of those together, I should get the two of those added together. Okay, twice the two of those added together. So 2 angle 2's and 2 angle 3's should give you back angle 5 and angle 6. Angle 5 and angle 6 is technically angle AOC. 2 is common to both of these, so factor it out. 2 into this goes angle 2 times, and 2 into this goes angle 3 times. Remember, angle 2 and angle 3 is technically angle ABC. Look at your diagram. Angle 2 and 3 is angle ABC. Alright? So therefore, angle AOC is equal to twice angle ABC. And that's what I was trying to prove at the very beginning. That the angle at the centre of the circle, so angle AOC, standing on a given arc, the arc is AC, is twice the angle at the point standing on the same arc. So it's twice that angle up there. So that's what I was trying to prove. Okay, so there are your theorems, okay, the 19 theorems on your course. Lastly then, we're looking at the corollaries. So there are 5 corollaries, alright? And remember, a corollary is just a follow-on from a theorem. You don't need to go learning them off by heart, but you do need to understand them and you do need to know when to apply them. So, corollary 1. A diagonal divides a parallelogram into 2 congruent triangles. Okay, we know that, and we're able to prove congruency for each of those. Corollary 2. All angles at a point on the circle standing on the same arc are equal. So in this diagram here, angle B is the same as angle D because they both sit on the arc AC. So that's all that's stating there. The converse of that corollary is if the angles at points on the circle are equal, then they must have been standing on the same arc. So that's the converse of corollary 2. Corollary 3, each angle in a semicircle is a right angle. That's because the angle would sit on the diameter, so it must have been a right angle, because the angle at the centre of the circle is twice the angle at the circumference, standing on the same arc. So the angle on a diameter is 180 degrees. So if there's an angle at the circumference sitting on the diameter, well then it must have been 90 degrees. Corollary 4. If the angle standing on a chord BC at some point on the circle is a right angle, well then BC must have been a diameter. Because if that's 90 degrees and it's sitting on the chord BC, there's the arc B to C as well. That must be 180 degrees because the angle at the centre of the circle is twice the angle at the circumference standing on the same arc. And they are both standing on the arc BC. And finally, corollary 5. if ABCD is a cyclic quadrilateral. Remember, a cyclic quadrilateral is a quadrilateral that is trapped inside a circle, and each vertex of the quadrilateral touches off the sides of the circle. Okay, that's a cyclic quadrilateral. So if ABCD is a cyclic quadrilateral, then opposite angles will sum to 180 degrees. It doesn't mean that opposite angles are equal. They're not equal. They will just add together to give you 180. So like this red angle here plus this red angle, they're opposite to each other. They will add up together to be 180 degrees. That's just what I've stated here. And angle A and angle C will add together to give you 180 degrees as well. Okay. The converse of Corollary 5 would state that if the opposite angles of a quadrilateral add up to 180 degrees, well then it must have been a cyclic quadrilateral. Okay, and i.e. what's a cyclic? It's where the vertices of the quadrilateral are lying on the circle. Okay, so next I want you to look at the following questions and do these, and then pause the video. Okay, so question 1. Question 2. These are going to use your proofs now, and a lot of it will either be using similarity or congruency to prove them out, or your knowledge of circles, radii, circumferences, angles. Question 3. Four. 5. 6. 7. 8. And lastly, 8. Okay, pause the video, do those questions, and then come back and look at the solutions. Okay, question 1. So part A, it said to find angle ABC. Okay, so I've just redrawn the diagram. All right, 115 degrees is labelled in the diagram. Therefore, that must be 65 up here because it's a straight line. If that's 65, that's 65 because they are corresponding angles. See those two parallel lines? That makes those two angles corresponding. So angle ABC is obviously 65 degrees as well. Part B, the triangle is isosceles. All right, so therefore, if angle B is 65, angle C is obviously 65. If you add the two of those and take your answer from 180 degrees, you'll get the angle up at the top. So therefore, angle BAC, the one up at the top, is 50 degrees. Question 2. So what did they tell us? Or what are we trying to find even? We're trying to find angle OYZ. So OYZ is this angle here. All right, I want to find that. So fill into your diagram what you know. Okay, they told me it's an equilateral triangle. So angle X, Z, Y, all of that is equilateral. Equilateral triangles have all equal angles. So they're all 60, 60, 60. So that means that's 60 degrees there. Now, if that's 60 and it's an isosceles triangle, or sorry, if it's 60 degrees, and we also know that the angle at the circumference standing on the same arc is equal to half the angle at the centre. So there's the angle at the centre of the circle. So that must be 120 if that's 60. Okay, the angle at the centre is always going to be twice the angle at the circumference. Or the angle at the circumference is always going to be half the angle at the centre, provided they both stood on the same arc, which they do, which is ZY. So that's 120 degrees. I also know that O to Y is a radius and O to Z is a radius. So that means the two of those are also equal in length. So that little triangle is isosceles as well. So if that's 120 degrees, take that from 180 and you get 60. That means this angle here plus this angle here must be equivalent to 60. Divide it by 2 and you get 30 each. So I've now proven that angle OYZ is 30 degrees. Question 3. These were true or false. So there's your diagram. Now, in my diagram, I'm always going to label everything I can. So it's a parallelogram that you were given. So parallel sides or opposite sides are parallel. This angle is the same as that one because they're vertically opposite. This angle here is the same as that one because they're alternate. This angle here is the same as that one because it's also alternate. And in a parallelogram, the diagonals bisect each other. So that means this is the same length as that. And this one is the same length as that one. But it does not mean that all 4 of those are the same length. It doesn't. Okay? So, first one, AB is the same length as CD. That is true. Why? Because opposite sides in a parallelogram are equal. Angle CDO is equal to angle BAC. So, CDO, this angle here, they're saying, is equal to angle BAC. BAC is this one here. So they're saying that angle there is equal to that angle there. No, it's not. You can see from my diagram, they're not the same angle. False. They're not alternate to each other. The length of DO is equal to the length of OC. That is also false. DO is here, and this is OC. They're not the same length. Okay? False, and there's your reasoning. DO is half the diagonal DB, and OC is half the diagonal AC. But the diagonals are not necessarily equal. Angle COD is equal to angle AOB. That's true. So COD, C to O to D is this angle here. And that's equal to angle AOB, which is this one here. They are equal because they're vertically opposite angles. There's your reasoning. And lastly, the length of CO is equal to the length of BO. That is false. So CO, that is not the same length as BO. And again, your reasoning, CO is half the length of AC and BO is half the length of DB, but DB is not the same length as AC. Question 4. You were to prove that triangle DAC and triangle ABC are congruent. So it's proving one of the 4 axioms. Okay, so I've highlighted the triangle in green and the triangle in orange there. I'm trying to prove that they are congruent to each other. So what do I know? It's a parallelogram, first of all, so opposite sides are equal in length. Okay, and then you're trying to look for angles, okay, or sides, whichever you can get from it. So if I go trying to prove side, 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 AB is the same length as DC because they're opposite angles in a opposite sides in a parallelogram. The length of AD is equal to the length of BC because they're opposite sides of a parallelogram, and the length of AC is common to the length of AC. They have a common side. Therefore, the 2 triangles are congruent by side, side, side. Alternatively, you could have proven a different axiom of congruency. Okay, you could go with this axiom either if you want. So again, they're the 2 triangles. So this time I'm going to try and prove angle side angle. So angle DAC is equal to angle ACB because they're alternate. The length of AC is equal to the length of AC, it's a common side. Angle ACD is equal to angle BAC because they're alternate. Therefore, the 2 triangles are congruent by angle side angle. You could also go off and try and prove side angle side as well. The only one you're not going to be able to prove is RHS. Question 5. Part 1, the answer is isosceles. They are isosceles triangles. Part B, then, you wanted to prove that triangle XYW is congruent to triangle YWZ. Okay, so let's look at the 2 triangles. Okay, and what do I know about them? Well, they both have a right angle. That side is the same length as that side. And they both share this common side in the middle. So, the length of XY is equal to the length of YZ. That was given. It's the hypotenuse. That was given. The 2 little strikes taught me that. Angle YWX is equal to angle YWZ because they're both 90 degrees. That was also given. The length of YW is equal to the length of YW because it's a common side that they share. So I've got a side, I've got an angle, and I've got a side. Okay, so you could go off and try and prove angle side angle, but actually, hang on, angle side, sorry, not angle side angle. Side angle side, no, actually, sorry, we can't prove angle side angle. So the only one we can actually prove for that is right angle, hypotenuse, and one other side, so RHS. Okay, because the order in which you prove congruency is really important. I'd have to have had an angle and a side and another angle touching off it in order to prove angle side angle. Or I'd have to have a side with an angle in the middle and another side on the other side of it in order to prove side angle side, which I can't, so the only one you can prove is RHS. Part C then says to explain your understanding of congruency. Well, congruency is when 2 triangles are identical. They're identical in size, they're identical in the length of their sides, and in the size of their angles. Question 6, you were asked to prove that angle x plus y plus z is equal to 180. So here was your diagram. All I was given was x, y and z. Well, if I want to get this angle in here, it's going to be 180 degrees minus z, because that's a straight line. If this is y, well then this angle in here is going to be 180 degrees minus y. And if this is x, well then this one in here is going to be 180 degrees minus x. I now know that this angle plus this angle plus this angle should add together to give me 180 degrees, because they're the three angles in a triangle. Okay, so that's what I'm doing next. So 180 minus z plus 180 minus x plus 180 minus y is equal to 180 degrees. Tidying that up, you're going to get 540 minus z minus x minus y equals 180. I'm bringing the minus z minus x minus y over onto the other side, and I'm going to bring the 180 onto this side and subtract. So I end up with a positive z, a positive x, positive y is equal to 540 take 180 is 360. And that's what I was trying to prove. Okay, they said prove that x plus y plus z is equal to 360. Question 7. Okay, I want to find angle COB. So there's your diagram. Triangle COB is isosceles. Why? Because CO, the length of CO is equal to the length of OB because they're both radii. If I know that that's 50 degrees there, well then this is obviously 50 degrees. If I know that's 50 and that's 50, if you add the two and take it from 180, you'll get the angle that we're looking for. So angle COB is 80 degrees. Part B then said find angle CAB. So in the overall triangle, I now know that that's 50 degrees. This is a right angle. Why do I know that? Because this is a diameter because it goes through the centre of the circle. Okay? If that's a diameter, well then this is an angle in a semicircle. And all angles in a semicircle that are touching off the circumference, that's 90 degrees. So if that's 90 and that's 50, add the two together and you'll get the angle up at the top. Take it away from 180. Part C. So I want to, the reason as to why angle BAD and angle BCD are equal. Well, they're equal angles because they both stand on the same arc BD. So that angle is the same as that angle because they're the arms of this angle and they're sitting on the arc BD. And the arms of this angle, there's one arm, there's the other arm, they also sit on the arc B to D. So that's why both of those angles are equal. Part D. I was to prove that triangle BAE is congruent to triangle DEC. So here's my diagram and I'm labelling everything I know. So you're thinking of your 4 axioms of congruency. I'm not going to be proving RHS anyway, alright, because I don't have enough information. I'm not going to be able to prove side, side, side either because, just make a quick note of this. See the point E there? E is just the intersection of A to D and the intersection of B to C. E is not the centre of the circle. They did not tell me it was. You can't make the assumption that it is. So E is not the centre of the circle. Alright? So that means A to E is not a radius. E to B is not a radius. E to C is not a radius. And E to D is not a radius. So don't make the assumption that it is. So what do I know? I know that the length of AB is the same as the length of CD because that was given to me in the question. I do also know that this angle is the same as this angle because in part C of the question I was able to state the two of those are equal to each other because they both sat on this arc BD. I also know that this orange angle is the same as this orange angle because they both sit on the arc AC. Okay, so now looking at what I've just figured out, I have an angle, a side and an angle. I have an angle, a side and an angle. So I've now proven that they are congruent. So just make sure your labelling is all accurate. And your reasonings are there as well and visible. So triangle BAE is congruent to triangle DEC by angle, side, angle. Okay, lastly then question 8. I am trying to prove that triangle AOC is congruent to triangle DOB and you're thinking of your 4 axioms. I'm not going to be able to prove RHS anyway, definitely not. And looking at my diagram, I'm not going to be able to prove side, side, side because I do not know what the length of AC is and I don't know what the length of BD is. Okay, I can't state that they're the same, they're not. Right? So what do I know? O is the centre of this circle, so therefore OA is a radius, OD is a radius, OB is a radius, and OC is a radius. So they're all radii, which means they're all the same length. I also know that that angle there is equal to that angle there because they're vertically opposite. That's all I know about this. I know nothing about this angle and this angle, bar the fact that they are the same angles because it's an isosceles triangle. But I don't know anything about these two angles in relation to these two angles because those two lines are not parallel either. You're not told that they are, so you can't assume that they are. So you're not going to be able to pull out alternate angles or anything like that. Okay? So what I've marked in this diagram is the only information you know. So that means I have a side, I have an angle, and I have a side. A side, an angle, and a side. So what you're labelling, AO is the same length as OD because they're both radii. Angle AOC is equal to angle DOB because they're vertically opposite. And the length of OC is equal to the length of OB because they're both radii. Therefore, triangle AOC is congruent to triangle DOB by side angle side. You could also try and prove angle side angle. Hang on, no, that should be, you can't. You can't prove angle side angle because you don't have enough information to do that. So that should be, couldn't also prove that. Alright? So you can't prove anything other than side angle side for this particular question. Now, in your exam papers, just to get a little bit more practice of theorems and when to use them and your corollaries and axioms and all the rest, I want you to do the following work in your exam papers. Okay, so 2019, there's 3 questions that came up there. 2018, there's 2 questions. 2017, you're going to do part B of question 8 and question 9. 2016, there's 1 question. 2015, there's 2. 2014, there's 2. 2013, there's 2. 2012, there's 2. And in 2011, there is 1 question. That's all based on geometry, theorems, axioms, and corollaries. Okay, so go and do those questions. All right, work your way through them.